Hello, my name is Daniel Richardson, and for this TMU, the second one, we will be discussing binomial distributions, and those are distributions that have two possible outcomes. So for this, I took from the essential bundle that the class has been working with, and I chose to pick from the stores that people shopped at. So we have things like Sacramento Natural Foods Co-op, we have Winco, and I chose that Rayleigh's was going to be our metric of success. So we wanted to see how many people were shopping at Rayleigh's, and that means that all others were marked as failures. So again, that does not mean that one is better than the other. Just reiterating, that means that we were testing for a success and any others were marked as failure. So saying a lot. On this spreadsheet, I inputted the data. So I copied the data and I pasted it here. And I proceeded to mark through and mark all failures with an F and all successes with an S. So we can see that Rayleigh's and Rayleigh's are S, S, S. So our success total is 8. We had 8 successes, and that means we input that data. So we have 8 divided by 35. And the probability of success is 8 divided by 35, which equals 0.2285714,286. So we have probability of success over here. Determine the probability of success from your data. Note, you can find the probability of success by using a fraction. So we did that. Next, we were supposed to determine whether it's discrete or continuous. So for a little bit of clarification, continuous are things that are measured. So usually when you are looking at continuous, you could be measuring height or some other unit of measurement. And discrete is something that can be counted. So this is something that can be counted. We are counting the amount of Rayleigh's that people have visited instead of possibly the distance that people travel to their grocery market. So we are going to mark this as being a discrete variable because it is a countable number of possible values. Now that you've identified a random variable and a probability of success, create a binomial distribution example with all the parts. So we're going to move over to a different tab. And you can see here that we have created a binomial table. So we have taken the information that we gathered from here. So we have the probability of success, which is marked with a P. And then we decided to play around with this number. I chose 40 times to check because that does give us any lower than this. And you do not have a 0 possibility on 0, which is very interesting in itself. If you go low enough, you are almost guaranteed to, well, not guaranteed, but it goes down to 0.004 as the lowest possible number. But so when you have 40, what is this called? Trials. So when we have 40 fixed trials, we're able to have zeros on either end. That's not really a requirement, but I thought it'd be nice to have. So here we have our binomial distribution. So we have the number of trials and the probability of success. And now we're able to sort of examine this binomial. Based on your example, justify why there are a fixed number of trials. I kind of did that a little bit. For us, the fixed number of trials are important because we do, when creating a binomial, it is important to recognize that you are creating groups of tests, and you can do 40 sets of 40 trials. You could do this, you can continue to do different experiments, but it is that you are calculating based on a group of 40. And so you can see that when you do 40, when you ask 40 people, your chances, these are your chances of finding somebody that goes to specifically a Raley's as compared to other shopping markets. So we have these 40 trials. 2 outcomes based on your example, justify how you have 2 outcomes. So we either have the success of going to Raley's or a failure of going to any other store. And justify how you have 2 outcomes. That would be it. That's justification enough. The 2 outcomes are either you do have a success or you have a failure. These are all independent. You can ask as many people as you would like whether or not they go. So we're talking about independence. This is whether or not the experiment, the variables are affect one another. And this is a situation where if you ask someone what store they go to, whether or not they go to Raley's does not necessarily influence whether or not the next time you do this test, whether or not the next person goes to Raley's. So, or it can even be that if you did this on a weekly basis and you continued asking the same people, just because they go to a Raley's does not mean that next week that they would also go to the same store. They could be more convenient to go to Walmart that week. So they are independent. So explain why it is important for the probability of success to be the same for each trial. This part I don't fully understand, but I would imagine that it is probably very important to have the same probability of success. Shouldn't change, because when you are experimenting, I don't know, I might need to come back to this. Expand your example by writing probabilities that you can calculate, then include the following greater than. So we are able to see that X is less than or equal to this. So we can change that because if we change, so that is we're able to see that if we shift this around, you can choose different metrics by which to measure less than or greater than. So we can have, if we wanted to see what the chances of, so we're going to go back to less than. If we wanted to see what is our chances of having 7 or less people go to Raley's, we would see that our chances of these totals of 7 and less are 0.2756. And then we have greater than or equal to, and you're able to see that we can shift this over here, and you would have 11 and up. So the chances of having 11 and more are actually very interesting. So we have 29.61. And that's different because you have all these zeros. So while before we were dealing with a different set of numbers, it sort of evens out because of the zeros. And then in between. So we can have an in between over here. So what's the chances of finding somebody who shops there between these two numbers, so 7 and 11, or we can shrink it down even more to 8 and 10. And so we have between 8 and 10, finding there is 0.4283. Calculate and interpret the probability you stated above, showing how you would use GeoGebra to compute each probability. Oh, I was supposed to write that out. Oops. All right, and that is all that we have for now. I will probably be back with another video explaining this. Oh, Razor. In the reflections. So thank you very much.